we're going to take advantage of the fact that these 4 numeric types happen to form a nested sequence of bigger and bigger sets. And we're going to do it this way. First, we're going to find our chalk. There we go. We're only going to have 4 rows for numbers in the table. So we're going to forget about type signatures, and we're just going to have integer, rational, real, complex. And if you remember the way they build up these types in the book, for minus, to subtract 2 integers, we just use schemes minus. And for rational numbers, we had something called minus rat. And for reals, we just used schemes minus. And then for complex, we had something like complex minus. Or maybe it was just C minus. Right? Well, what if we get an integer minus a rational? What do we do in that case? Well, the next thing we're going to do, besides plus minus times divide, we're going to have 2 more columns in our table. One is called raise, and one is called level. Okay? Level is going to be used to tell us about this subset relationship. What's a subset of what? And the way it's going to do that is we're not even going to put procedures in here. We're just going to put 1, 2, 3, 4. Okay? Bigger number, bigger set. Okay. Raise says for each level, how do we convert this to the next level up? Okay, so this is going to be n maps to make rat n1, right? To get an integer to a rational number, we do integer divided by 1. That's a rational. Okay? The raise procedure for rational has to raise it to a real number. And how do we do that? We do rational number maps to divide the numerator of R by the denominator of R. Okay? So this gives us a floating point representation of that integer, because this is the scheme built-in divide. Actually, when I say that, I'm lying. We went to some pains to make sure that when you say slash, what you get is not an exact rational, because many versions of scheme, probably most by now, actually do support exact rationals as a built-in type, but ours doesn't on purpose so that I can give this lecture. To raise a real number to a complex number, what do I do? X maps to make complex x 0, right? So it's x plus 0i. Or if you're an electrical engineer, x plus 0j. Complex, we leave this slot empty. There's nothing in here, because there's nothing to raise complex to. That's as far as we get. Okay? So now, we're calling a dyadic operator. We get 2 operands. We extract their types, and that gives us a type signature. So what our operate procedure has to deal with is still, to begin with, a type signature. Then what it's going to do is for each word in that type signature, it's going to look up level. So if we have, let's say, an integer and a rational, we get back 1 and 2 respectively. Okay? Whichever of those numbers is smaller, we look up raise for that data type and apply it to the value that we have. So if what we have is an integer, well, let's say an integer plus a complex, just to make it more interesting. So I have an integer and a complex. The answers are 1 and 4. 1 is smaller, so I call raise on my integer. And that gives me an exact rational. Like, let's say it's 5. I get 5 over 1. Okay? Well, now I recursively call apply generic, which is the book's name for what I've called operate here. And now I have a rational and a complex. So we look at their types. We look at their types, rational, complex. And then we map level on that, type signature, and we get 2, 4. The levels are still not equal. So I do the same thing. I find the smaller level, which is the rational number, and I call raise on it. And that converts it to a real number. So I started with 5, and then I had 5 over 1, and now I have the thing that prints as 5.0, which is 5 in real representation. And now I recursively call apply generic, and I have a real and a complex, and I look at their levels, and that's 3 and 4. Still not the same. So I take the smaller one, which is 3, and I raise that operand again. Now it's a real number that I'm raising, so I say make complex 5.0, 0, and I get the answer 5.0 plus 0i. And now I call apply generic again, and we look at the levels of the two types. The two types are now complex, complex. So their levels are 4, 4. They're the same. So now I can go ahead and look up how to subtract two complex numbers and apply that procedure to the two numbers. Okay, questions about that? Yeah. Okay, good question. His question is, what if instead of just raising one level at a time, I make procedures for every pair of types that raise the smaller one to the higher one? We could do that. It would give us 3 plus 2 plus 1, 6 procedures to write instead of 3. That's not the end of the world, 6 compared to 3. But it's a little more elegant since these things are subsets of each other to kind of take advantage of that. But we could do it that way, you're right. So we could have type signatures in the table only for the raise operator. And that would directly raise integer to complex or whatever. That would actually be better in one way, because this mechanism that I've just described to you has a drawback. And that is, if I take the exact rational number 1/3, or even, it turns out, the exact rational number 1/10, and convert that to real number computer form, I get an inexact answer. Right? With 1/3, that's true even for ordinary decimal elementary school arithmetic. You get 0.33333333, et cetera. Right? And so if we represent it internally as 0.333333, that's not exactly right. The fact that not exactly right answers cause a lot of trouble. Because you're thinking, well, 0.33333333, that's close enough. That's more precision than I care about. But that's true if you only ever do one operation on your data. Typically what happens in a numeric, especially in scientific computation, is you multiply that 1/3 by something, and you add something else, and you divide by something else, you add something else and you subtract a third, and you get something that's like way wrong. Well, I'm sorry, no you don't. You get something that's way wrong if you do something like taking the tangent of one of these inexact values. Why? Because the tangent function has a huge slope, right? Everybody remember that from high school? Zoop, and then goes back down here and goes zoop again, right? So except for right near those zero crossings, a teeny little error in the argument to tangent turns into a huge error in the return value from tangent. Okay, and if you use that in a more complicated computation and that error propagates, before you know it, you have 0 digits of precision. Avoiding that is the job of a field called numerical analysis, which very few people actually choose to go into. But it's important that some people go into it because otherwise our next generation of computers will just produce crazy wrong answers, which is what used to happen until Professor Kahn in our department sort of laid the groundwork for dealing with imprecision in computers in a systematic way.